David Ken here with another question bank question in topic 4.3. We start off with a statement of the principle of superposition. Superposition is all about what happens when waves overlap. So we'll say when two waves overlap in a medium, the medium takes on the shape of the sum of the individual waves. So at any point in the medium, the shape of the medium is the sum of the shape of the waves that are in the medium at that point, at that time. We'll use that idea to answer the rest of the question. Two loudspeakers, S1 and S2, are connected to the same output of a frequency generator. So we're just sending out a sine wave into the air. It just goes boop from both speakers. Placed in a large room, so we're going to ignore any echoes from the walls. And sound from both sources travels off in all directions, including the direction towards point P and the direction towards point M. The distance from S1 to P is 560 centimeters. The distance from S2 to P is 580 centimeters. The distance from S2 to M is 550 centimeters, as is the distance from S1 to M. That's also 550 centimeters. It didn't say so in the diagram, but it does say so right here. M is a point that's a distance 550 centimeters from both S1 and S2. The sound waves of wavelength 40 centimeters and amplitude A are emitted by both loudspeakers, and we want to state and explain what happens to the loudness of the sound detected by a microphone when the microphone is moved from M to P. Okay, that's a lot of setup for what is really a straightforward idea, and that is that we're going to detect sound at M and then bring that detector over to P and observe the changes in the sound along this path. All right. The first thing that we need to recognize is that at M, the path from this speaker to M is the same length as the path from this speaker to M. What that means is that at M, both the wave from S2 and the wave from S1 will be doing the same thing at the same time. By the time the wave from S2 reaches M, it's going to be following the same pattern as the wave from S1. Basically, there's no path difference between the two. So we can say that at M, we can say at M, the path difference is 0. Therefore, we experience constructive interference. At M, and a loud sound is heard. At P, it's a little bit different. At P, the waves from S1 travel 560 centimeters, but the waves from S2 travel 580 centimeters. Therefore, it takes them a little bit longer to arrive at P, and they wind up doing something slightly different. The path difference between the two is 20 centimeters, which is half of the wavelength. That means that by the time the waves from S2 reach P, the waves from S1 will already have traveled an extra half a wavelength onto somewhere else, and we'll be looking at a different portion of the wave by the time that they all meet together. So at point P, the two waves will be doing different things. When the waves from S2 are at a peak, the waves from S1 will be at the opposite portion of the cycle, which is a trough. So they're always going to be out of phase at P because of that path difference. That's going to result in destructive interference. So we can say, meanwhile, at P, the path difference is half a wavelength. Therefore, a quiet sound is heard. So finally, we can conclude that the sound will start loud at M and gradually become quieter at P. Right, so continuing on with the same question, we're going to change the situation. So referring to the same diagram, the amplitude of the wave emitted by S1 is now increased to 2A, so the amplitude is doubled. Meanwhile, we'll leave the wave emitted by S2 the same. We want to deduce what change, if any, occurs to the loudness of the sound at M and at P when this change is made. So we'll start with M. So the sound at M becomes louder. Because the waveforms at M still add. Basically, the idea here is that just because one wave has gotten taller, they're still doing the same thing at the same time. They're still both peaks at the same time. They're still both troughs at the same time. So their displacements are still adding. Therefore, there's more total energy in the resulting waveform. So because they all still add together, but we're adding more, there's more total energy in the waveform. At P, the argument is a little different, but the result is the same. At point P, the sound becomes louder still. The idea here is that the waveforms are no longer equal and opposite. They're still opposite, but not equal. Therefore, there is a residual waveform at P. So because they're still doing opposite things, but one is bigger than the other, when they cancel, they don't totally cancel. And so there's still some information from the wave that came from S1 arriving at P. They don't totally cancel out. And so even though the sound at P will be quieter than the sound at M, the sound at P becomes louder than it was before we made the change to speaker S1. All right, moving on to the last question. The two speakers are now replaced with two monochromatic light sources. State the reason why bright and dark fringes are not observed along the line PM. Bright and dark fringes would be the light analog of these loud and quiet sounds that we're hearing. Bright and dark fringes are the result of superposition for light. And the question is implying that the phenomenon that we observed for sound is not going to happen with light. And they want us to know to explain why. The key goes back to here. Same output. We've hooked the speakers up to the same output from the same frequency generator, so we know the wave coming out of S1 and the wave coming out of S2 are the same. But with light, this is something that's trickier to produce. You can't just turn on a light bulb here and turn on a light bulb there and expect them to be doing the exact same thing at the exact same time. The colors might be the same, but the phase differences are going to be totally different. And in fact, if we're talking about something like an incandescent bulb as opposed to a laser, then the light coming out of all of the different surfaces in the bulb are going to be incoherent with themselves. So not only are the two lights going to be doing incoherent things, the individual bulbs and the light coming out of the bulbs itself is incoherent. So it's emitting all kinds of different waves at all kinds of different phases. And not just within the one bulb, but across the two, which allows us to say that, it allows us to say there's no reason to expect the light sources to be coherent. Basically, there's no reason to expect the light sources to start out doing the same things at the same times.